I like it.
Okay, but tell
We're doing the show. The show.
Thomas is there.
We're gonna get
That's straight.
Tuesday.
All right. So we're going to finish up with curve sketching for derivatives. We'll get some more practice with that today, especially if I give you a first derivative graph and I ask you information about the original functions such as relative max, relative min, concave up, concave down, point of inflection of the original graph. So yeah, we'll do a couple practice with that. And then we're going to move on to our last topic of the unit, which is optimization. It has a word problem feel to it, similar to related rates, but we're just going to focus on 3 types of problems, and I'll give you the big picture so that you can keep that in mind. And really, just finding critical points. It's just the setup. Sometimes just needs some practice to get that set up. But the calculus is easy because it's just power rule finding derivatives. And then on Monday, we will continue finishing up on optimization. We can start our test review as well on Monday. We do have homework for optimization, but I'm not going to get through every type of problem with you. So I'll make the homework due for next Wednesday. Okay, I'll definitely send out a reminder Tuesday so that you can get that turned in on time for Wednesday. Tuesday is PSAT day, so early release, and then Wednesday full day of review, Thursday full day review, and then Friday test. And I plan on having help sessions on these 3 days. Okay, so I'll have a help session Wednesday morning, Thursday morning, and Friday morning. Okay. All right, so if you guys can turn to page 6 in your packets. Let's finish up number 4. Let me recap what we've accomplished with number 4, and we'll finish number 4, and then we'll do another problem similar to this. Okay, so we start off with the derivative graph. The important thing is that we label our derivative graphs. I think it's helpful just to have these guidelines where we understand what we're looking at, that we're not getting thrown off by the movement of the graph. We want to focus on the location of the graph. Is it on the x-axis? Is it above the x-axis? Is it below the x-axis? Really all you care about to begin with, okay? So at the beginning, you're going to plot your x-intercepts, okay? So your x-intercepts will be your candidates for relative min and relative max of your original graph. So you start off looking at your x-axis and picking out your critical points, okay? So -2, 1, and 3, we went ahead and we placed them onto our slope sine line. And then we look at where our graph is located. Don't look at how the graph is moving, just look at where the graph is located. Here, the graph is located above the x-axis, so anything to the left of -2, we want that portion to be positive, right? We're just matching the symbol that we see on our to the left of our derivative graph. Okay, between -2 and 1, it's still above the x-axis, so we want to match that symbol. Between 1 and 3, below the x-axis, we'll match that symbol, negative slope, and then to the right of 3, above the x-axis, a positive slope. So now all you're going to do is you're going to create a graph that has these exact behaviors as how the arrows are pointing. Okay, so I want my graph to rise and flatten out at -2, continue rising until it hits a relative max at 1, decrease to 3, and rise above it. So I'll rise after that, a relative min at 3. So you're going to create a graph that has these that has the direction of these arrows. Okay. So if you can sketch a graph for this, then it doesn't matter where it is in terms of, is it all above, is it all below the x-axis? If you can get these behaviors to work out, then that's what I'm looking for on the test. Okay, I'm looking for you to sketch a graph that has the shape and the direction that these arrows are presenting. Next up, we also want to be able to pull concavity information of the original graph, but we're not going to rely on the original graph because the original graph is based off the derivative graph, so it's not as accurate as it could be, which is fine. But we need to learn how to pull concavity information of the original graph from the derivative graph. Okay, so what you do here is now you're going to be paying attention to the peaks and valleys of your derivative graph. The peaks and valleys of your derivative graph. So -2, 0, and 1. Those are your points of inflection. And then we can go ahead and put those onto our concavity sign line. And now we have to fill out concave up and concave down. And this is where I see some students struggling for a good reason. And the reason why is because when you want to fill out your concave down and concave up, a lot of students want to look at this and say, well, that looks like concave up, concave down, concave up. But this is not the original graph, so we can't rely on the curvature that we normally would as if we're looking at the original graph. So the way that you have to approach it is you have to look at the slope. Okay? The slope of the derivative graph is going to translate to the concavity of the original graph. Okay, so concave down. Negative slope is going to translate to concave down. And here again, we have negative slope, concave down. Anything that has a positive slope off of the derivative graph is going to translate to a concave up on the original graph. Okay. And just to convince you of this, the curvature here should match the curvature that we potentially have created with the original graph, right? So if it really is concave down, then it should look like that on my original graph, on my graph that I created based off the F prime graph. Right? Concave up, the shape should resemble that of concave up, and it does up until 0. And then from 0 to 2, concave down, we do see that visual shape of concave down, and then concave up is here. But the way that we pull that information off of the derivative graph is not the same way that we pulled it off of the original graph. So now let's create a second derivative graph. The way we do that is go ahead and label what you're dealing with here. Anything above the x-axis is concave up. Anything below is concave down. Anything on the x-axis are your points of inflection. And then go ahead and plot your x-intercepts. Your x-intercepts will be where your points of inflection are on your F double prime graph. -2, 0, and 2. And now what you're going to do is you're going to match the location with the symbol. Okay. So I see the symbol here, the location is below, so I want the graph to live below the x-axis. And then these anchor points kind of helps you know where your graph is going to have to move towards. Okay. A common mistake that I see students make is they feel like they have to get these shapes, these curvatures to show up on the second derivative graph, but we're not going to worry about that, right? The curvatures has already been taken care of off of the original graph. You're just going to make the graph live in these locations. Okay, so that's concave down. That's obviously below the x-axis. So I'm just going to make the graph rise to that point because I need to, because I have the point already defined. And then above the x-axis, concave up above the x-axis, I'm just going to make my graph rise and fall. I know it kind of looks like concave down to you, but really we're just making the graph live in this upper region. But that point is telling us we have to come back down at some point. So that's why it kind of has that loop downward. The location is what we're really after. Okay, concave down, that's below the x-axis. So we're going to make the graph dip below the x-axis, but that's to come back up because we already have that point identified. And then to the right of 2, concave up above the x-axis. Okay. I think I see some from previous years, I see some students, they want to work in a lot of curvature to make it fit the curvature that they see here. But also understand something is that as you move from derivative or from function to its derivative, you're going to have less curves, right? So you're going to experience the most curves at the original function, but each time you find the derivative, you're going to be 1 degree lower, so you're going to have less curves. So once you get down to the second derivative, you're going to have a much simpler looking function than what you started with. Okay, so now it's the easy part. The easy part is filling the characteristics, because if you have these slope and concavity sign lines filled out, you're really just translating all those symbols into intervals. Okay, so see if you can fill out those characteristics. I'm going to have us do a full practice of this on page 8, and I want to walk around to see, can you start with a derivative graph, create the slope sign line, create a graph that resembles the arrows that you see, and then from the first derivative graph, can you gather your concavity information, and then finally sketch your second derivative graph. Okay, so characteristics should feel easy, especially if you have your slope and concavity sign lines all identified. Right, increasing in these 3 subintervals, -infinity to -2, -2 to 1, 3 to infinity, relative max at 1, relative min at 3, concave up in these 2 subintervals, concave down in these 2 subintervals. There's a change in concavity in each of these critical points, so we have 3 points of inflections. And if I give you the derivative graph, the best you can do is give me the x values. Okay, I'm not going to ask you for the y values. We're not going to learn how to do that until second semester, especially off of the derivative graph. Okay, so why don't we try a full example of this? I'll leave this up here on the board so you can kind of use this as a model to help your steps. And then, so go to page 8, and we'll do this problem, and we'll do a graph from the derivative perspective. Okay, I'll come around and kind of check on your progress, and I do want us to have some level of comfort with this before I move on to optimization. Okay. So page 8. All you're doing from the sign line, slope sign line to the original graph, you're just going to follow whatever the arrow is telling you. So if the arrow is telling you to rise, you're going to make the graph rise. So in the end, your function graph should mimic exactly how your arrows are pointing directly.
They're still silent, but they can actually see those arrows. Yeah, so you guys see actually, yeah, I should. Doesn't matter which one's higher or shape on it. Actually, just one thing, it has to line. All the way to the scale. You're just gonna pick up your x-intercepts, just your x-intercepts. It looks like concave, right? You got a lot of slope, so this is concave. Negative slope is concave. Yeah, so there's a relative max of -4. We just make that a low height point, a low point, and that
Doesn't matter which
it
one's.
doesn't matter.
Okay.
So you're just gonna make the graph follow those arrows.
Okay.
This doesn't matter, that's all. As long as you get to that. Yeah, and so there's a relative amount. It doesn't matter where. I like. Negative number. Yeah, just. Doesn't matter which one is higher. So you have to pick the point here. That's the way it's originally. Doesn't matter where it was, big number, max -4.
All right.
That looks good. I don't like how, I don't, doesn't matter how long.
Like, or double prime? Yeah. Single prime? Okay, once you x-intercepts. So if this is and everything above here is your increase. Everything is your decrease. And you start above. That means you're gonna increase it better. Yeah. Yeah.
I think it's. This is like, it's good. This is. This is.
from -4 to -150. It's below the edge. Okay.
Yeah, so behind the arrow, there's
Okay.
a nice little garage, and there's one side, if you see it, so there's one side. Here, now.
Yeah, see, this makes sense.
So you're good from here.
So it's right. Yes, that's real.
Five. Oh, the result is a nice kind of thing. So I don't think it's also line that's that. Yeah, I'm gonna figure out when it's five. I think so.
I think so, yeah.
Okay, so it's, so I.
I'm double checking it.
Okay, let's compare. So we pick out our critical points. Make sure you start off with your x-axis, x-intercepts. Those are going to be how you're going to get your slope sign line going. And then you look, don't look at the rise and fall of the graph, look at the location. Above the x-axis means positive slope. Below the x-axis means negative slope. Above the x-axis, positive slope. Below the x-axis, negative slope. And then you're just going to make your graph resemble the movement of these arrows. The arrows are rising to a relative max at -4, decreasing until a relative min at -1, and then rises until it hits a relative max at 2. Now your graph can be different locations. Maybe this relative max is lower than this one. It doesn't matter. As long as it has the same shape as my graph, it doesn't matter what the location is. Okay. Your graph needs to have 2 peaks and 1 valley. The 2 peaks are at -4 and 2, and the valley is at -1. Right. Now, the struggle with the interpreting is with the point of inflection, and with good reason, right? It just feels a little bit different in order to get there. So the first thing is you want to pick out your peaks and valleys. Your peaks and valleys of your derivative graph is where the points of inflection is going to live on your original graph. So your -2 and 1 will go onto your second derivative sign line. And now you got to decide, okay, what am I dealing with? Am I dealing with concave up or concave down? Now, I know this looks like concave up to you, but the way we interpret concave up, pulling that information from the derivative graph, we got to look at the slope. So you see that this is obviously a negative slope here. So negative slope is going to translate to a concave down on the original graph. Okay. Positive slope is going to translate to a concave up on the original graph, and concave down. Sorry, negative slope on the derivative graph means a concave down. Okay. And then once you have this in front of you, then you just have to be able to label above and below as concave up and concave down. Below, we'll first plot your x-intercepts, which are -2 and 1. Below the x-axis, to the left of -2, I want that region to be below, or the graph to be below the x-axis. So that's why my graph is living here. And between -2 and 1, above the x-axis, so it has to go up and move back down, but it has to all live in this region. And then to the right. Okay, we're definitely gonna get more practice with this next week, but hopefully this is becoming a little bit easier to manage. All right, and then just go ahead and fill out your characteristics. The characteristics is the easiest part, assuming that you got the sign lines correct. You're just pulling information from your sign line, just putting it into those characteristic boxes. Okay, go ahead and do that, and then we'll start optimization. All right, let's go to page 9. Okay, so let me highlight some big picture ideas with optimization. So we can kind of keep this in mind. The big picture is that you're really just trying to find a critical point. So think about what you do with critical points. You start off with your equation, you find the derivative, you set the derivative equal to 0, and you solve for x. Right? That's something that we've been doing ever since 3.1 when we did EVT. But now the challenge is trying to get this first step going. Okay, because once we get that first step down, because we may have to set up the equations and interpret the word problems in a way so that we can create these equations, and then we got to get the equation down to one variable. But then once we're there, then we're just doing cleanup. A lot of times your derivative is mostly just power rule. I mean, we may have some chain rules, but mostly you're just relying on power rule. But as easy as it sounds, we may need to do some cleanup, which we know how to do. We just have to. It just takes a little bit longer to get everything all cleaned up. But really, you're just going through power rule once you have everything cleaned up. Okay, so the big picture is that you're just finding the derivative, set that equal to 0, and solve for x. Okay. All right. So optimization is the process of finding the greatest maximum optimal solution, or the least value of a solution, the minimum optimal solution for some constraint, which must be true regardless of the solution. So optimization finds the most suitable value for a function within a given domain. So it doesn't matter if we're trying to find the maximum or the minimum value, or but just think of it in terms of we're looking just for the optimal value. Okay, and the steps will be the same whether we're doing maximum optimal solution or the minimum optimal solution. Okay, so here are the steps. We're going to first write the equation for the variable that you want to optimize. Okay, I'll talk about how we can decide which equation that we know we're going to have to find the derivative for. Okay, we're going to have to substitute to get the equation in terms of just one variable on one side. So that's the challenge, to get that right side just in terms of one variable. And then becomes the more straightforward part. We just get that equation set up ready for derivative, go through power rule, find the derivative, set equal to 0, solve for x. And then we just go back and read the problem to make sure that we're providing the information that they're asking for. Okay, so number 1, it says a manufacturer wants to design an open box having a square base and a surface area of 108 square inches. What dimensions will produce a box with the maximum volume? Okay, so the big picture, big idea is that we have a certain amount of material, but we want to create the box that has the largest space. And we want to kind of optimize that amount of material into something that is going to hold the most amount of volume. Okay, so the first thing we're going to do is we're going to pay attention to the keyword, whether this maximum, minimum, optimal. So we see that word there, maximum, and what is it describing? Maximum volume, right? So that tells you that you're going to be focused on, that's the primary equation. That is where you're going to try to get and cleaned up and get ready for derivative, and you're working ultimately with that volume equation. Okay, so we'll put a star next to volume, put a star next to V, because ultimately this is the center of our problem here, this volume equation. Okay, so let's look at this box here. How do I find the volume of a rectangular box? Yeah, length times width times height, right? It's drawn out for us here. So length is x, width is x, height is h. So x times h, x squared h. And the issue is the right side of the equation has multiple variables. So we're not going to be able to find the derivative until that right side is cleaned up. either everything in terms of x or everything in terms of h. Okay. So we need some support. So the support is going to come from the other part of the problem, that information that's going to give us in the problem. It says the manufacturer wants to design an open box having a square base in the surface area of 108 square inches. So this is going to give us information that's going to allow us to substitute our variable down to just 1. Okay, so surface area, 108 square inches. But we also need to build the surface area equation as well. So surface area, what does that mean? We're essentially finding the area of the surfaces. Okay, so how many surfaces are there in this open box? Usually it's 6, but it's 5 because there's no material at the top for the top of the box. So you're going to have a base and 4 sides, but there's not going to be any covering needed for the top of the box because it stays an open box. Okay, so we have 5 surfaces to worry about, and we're just going to add up the area of each of the surfaces. Let's start with the easiest one here, the base. Okay, what's the area of that surface? X squared, right? The base is just length times width. Okay, let's. How many vertical heights do we have, or vertical sides do we have? 4. Okay, what's the area of one of the vertical sides? XH. Okay, and how many, and then are all the vertical sides the same formula? Yes, right. So I've got to do 3 more of these. Okay, so really we're not really memorizing anything, right? We're just kind of looking at the wording and then just making sense of it, right? We're adding the area of the surfaces. Each area is the area of the surface. And we have 5 surfaces, so we're going to add them all together. Okay, so my surface area equation can be reduced and cleaned up to be just what? X squared plus 4xh. Okay, we do have a surface area value, so we're going to go ahead and make that replacement. So now we have to ask ourselves, well, how can this surface area equation help us out with this volume equation? And we got to decide, okay, which variable is going to be the easiest to solve for and replace. So let's start off with the surface area equation. Which variable do you think will be the easiest to get by itself? If we solve for x squared, we still got to deal with this x, right? So there's too many x's that's going to make it difficult to get that x by itself. I mean, maybe we could with completing the square, but it's just not worth the effort. So, but we only see one, what? There's only one h, so that should be easy to get that by itself, rather than having to deal with different x's all over the place. So let's just try to get that h by itself. Okay, I'll highlight that variable, and then we can make the substitution into the volume equation. Okay, so I'm going to subtract the x squared, then I'll divide the 4x. Okay, divide both sides by 4x. So here's my height variable isolated. All right, so now I have a perfect substitution for the h for my primary equation, right? Because my entire goal is to get my volume equation down to one variable. It could be all x, it could be all h, but we're just taking the path of least resistance here, trying to what's the easier variable to solve for, and whatever is easiest, that's what we're going to get by itself, and that's what we're going to try to replace. So we're going to replace h with this 108 minus x squared. So we're able to get our volume equation down to one variable. Okay, I'm going to write that over here. So v is equal to x squared times this entire expression. Okay, we are, at least we're down to one variable, so we're making progress. but we do need to get it to the point where we can eventually find the derivative. Okay? But right now, it does look a little messy. Let's just distribute through because we should be able to get this all the way to the point where we're only relying on power rule. We shouldn't have to deal with, quotient or chain or product rule. Everything should clean up nicely. Now, when you distribute the x squared through, you only distribute the x squared through the numerator, not the denominator, because denominator is 1, right? So it's really multiplying across. Okay, I'll distribute the x squared through. Okay, what else can I do to clean this up so that I only have to deal with power rule? I only have one term in the denominator, so I can just split this up into what? Into 2 fractions, right? That way I can kind of individualize each term and just handle them independently. Hey, you can use your calculator. 108 divided by 4 reduced to be 27. X squared and x can just clean up to be just x. I can pull that 4 out as what? That 4 in the denominator can be pulled out as 1/4, okay? And how many x's are left over? X to the cube, yeah. I got 4 above, 1 below. Take 1 from both sides. I'm left with x cubed. Okay, so now we have a nice clean equation. We just find the derivative, so now it gets easier. We find the derivative, solve for x. So when you find the derivative and solve for x, you're essentially finding the optimal solution. The optimal solution is always going to be where your slope of the derivative is 0, where your rate of change is going to be 0. Okay, so b prime. Okay, 27x becomes, we keep the 1/4, x cubed becomes 3x squared. We have our derivative. We'll clean that up, set equal to 0. Okay. Dividing by 3/4 is the same thing as multiplying by the reciprocal. Okay, do some cleanup here. 27 divided by 3 is 9. 9 times 4 is 36. So x squared equals 36. We take the square roots. There's a plus or minus that shows up. But only one x value makes sense, right? What's that? Positive 6, right? We're talking about length, physical length of a base of a rectangular box, so negative is not going to make sense. So that's out. So x is equal to 6. Okay, so as soon as you find your quote unquote answer, you still got to go back and read the problem again and just make sure that you're providing everything that they're asking for you to provide. But pretty much our work is done. We just have to make sure that we're providing what the problem is asking for. This is what dimensions will produce a box with maximum volume. So dimension is just width, length, and height. So we already have the x's, so we have length and width. So I just need to find height. Do we have a formula for height? Yeah. So you basically just have to kind of go back and just search for it because along the way you have to make a substitution. So there's going to be a height equation that's waiting for you to use. So I have one here, 108 minus x squared over 4x. Okay, replace the x with 6. Okay, that's going to reduce all the way to 3. So my dimensions, that will produce the optimal, that will produce the maximum volume with that restricted surface area. It's going to be 6 inches by 6 inches by 3 inches. Okay, a few minutes here. Let me see if I can squeeze in one more problem. This is number 10, page 10, number 2. Sorry about this problem. It's so grainy. So let me read it here. It says a rancher has 200 feet of fencing with which to enclose 2 adjacent rectangular regions. What dimensions should be used so that the enclosed area will be at a maximum? So we see that the word maximum is describing area. So we know ultimately area is going to be the equation that we're going to find the derivative for. Let's do a 2-dimensional picture of what you see there. And it's hard to see those variables, but it's going to be x along the horizontal and then y is along the vertical. Okay, so area. What's the area of this fenced off region? Close. Length times width, right? What's the length? Not x squared. 2x, right? X plus x, right? So length is 2x. Height or width is y, so just 2x times y. Okay. Now we're eventually going to find the derivative for area, but that we have 2 variables, so we need some help. So the help is going to come from the fact that we have 200 feet of fencing. So if I have 200 feet of fencing here, if I add up all the sides, that's related to what? We call that perimeter, right? So perimeter is adding up all the sides that represents these fences that we're going to be using. So perimeter is what? 4x plus 3y, right? Because we also have that fence in the middle as well, right? Perimeter is 200 feet, so we have that information. Is it easier to solve for one variable versus another? Not really, right? So I'm just going to solve for y because I just like to have my equation in terms of x. Okay, so just have you do a few more steps and then we'll stop in a minute. Okay, so what we're going to do is we'll take that equation and we're going to solve for y. So I'll do 200 minus 4x divided by 3. So that gives me 200 minus 4x over 3. So I'm going to take that and I'm going to replace my y variable, right? Because my whole point is trying to get my primary equation down to one variable on the right side. So now that I have 2x times something that's in terms of x, now I can just do the same thing that I did before with the previous problem. Distribute, clean up, get it ready for power rule, find the derivative, set equal to 0, solve for x. And that's our process. All right, so we'll pick this up on Monday. We'll finish optimization. We'll start test review. Tuesday, no classes. Wednesday, Thursday review, and then Friday test. I should be able to get back your quizzes on Monday as well. Okay, come up and get your phones. All right, say it again.